Good morning, evening, afternoon, or whatever time it happens to be for you all in Precalculus. For what we're doing today, we're working on 8.2.6. This is Friday, April 24th. Woo! One more week down. We have 6 more weeks of school about. Anyways, so with this, we're going to be talking about proof by induction, and one of the first things we're going to do is sort of show that the sum of the series of odd numbers, so that would be like 1, 2, 1, 3, 5, 7, 9, 11, so on and so forth, is equal to the idea of the n, which is the term number, squared. So as we look through this, we're going to sort of show it. And with induction, there are 4 main steps that we do. There's one that's not shown here, which is basically if you're given a completely blank slate and you need to be like, okay, find the sum of the series and prove that it's the actual sum. One of the things is sort of creating the rule between terms, which is sort of a missing step in proof by induction. But something you should do if you're just given a blank series of numbers and you have to be like, okay, I need to show what the sum of the series is, and this is how I'll do it. So one of the first things you do is you prove that your sum is true in the first case. And usually the reason why we choose the first case is because 1 is a very easy number to deal with. And so you prove that it works in the first case, and then you go on and you assume that when your case is any number, that it'll work for that number. So you assume the idea of n equals this value k. And then sort of the next point is you sort of assume, okay, if it works for that one, then it should work for the following one, and then you prove that arbitrary next case is true using the information, and then if it works, you've concluded that your rule holds up and you have proved your sum correctly. So when we do this, if we look at the odd number of terms, we're going to sort of go through this. So what we're going to do is we're going to first sort of idea of, well, it's the sum of the first odd number of terms. So we do n squared. N squared is 1. And what do you know? The sum of the terms is 1. So we have n squared equals 1. Our first term is 1. So we have 1 squared equals 1, 1 equals 1. And what do you know? We showed that work for step 1. Now, next two is that we're going to sort of write out each side. So as you see here, we have our 1, 3, 5 plus ... plus 2k minus 1. Now, what the 2k minus 1 means, that's going to be the next odd number in the series. So if you sort of want to know, like, okay, let's go with, we can try it for some of these terms that we currently have. So let's go with, let me turn off the book. But let's go with like n equals 5. Or like k equals 5. So the fifth term, if we think about it, which should be 9, let's test it in our thing just to make sure. 2 times 5 minus 1. So that'll be 10 minus 1, which equals 9. And that sort of matches up between these two things. So we have term 5 is 9. We got 9 using this formula, so we should be good. Now, what we're going to do next, so we write it out and we sort of have this idea that this is sort of true, because it would be 9 plus 7 plus 5 plus 4 all the way down, and we end up getting it equal to 25. So we're just sort of doing it in this general form with k. Now, what we do next is we're going to sort of, I put the idea, so instead of k, we're going to put in k plus 1. So when we do that, we sort of get the term before this final one will be 2k minus 1. And then this, we're going to have the next term, which will be 2 times k plus 1 minus 1 equals, instead of k squared, k plus 1 squared. Now, one of the key things that we do here is if we look at these terms, and we look at these terms, this section and this section are the same thing. Now, because we already have it sort of assumed as true here, we can actually just sub in, and so all of this is just k squared. So we end up with an expression that is k squared plus 2 times k plus 1 minus 1. And so when we do that out, we get, let me zoom in, so I can write bigger, or more accurately. So we have 2 times k plus 2 minus 1, and then this k squared stays there. And then when we do this, we get k squared plus 2k plus 1. Now, as we do that, we combine the 2 and the 1, and we're left with just a 1. And then this all remains the same. So we end up with k squared plus 2k plus 1 equals k plus 1 squared. And if we look at it, this is what we got for this side, and this is what this side is expanded. So therefore, we can say that our conjecture is true. So we have successfully proven that it works for k plus 1. And so since we've established it, we're good. And since we established it worked for the first case, and then for our anonymous case, we assumed it was true, and then we proved it for the one arbitrarily more case than the other one. Therefore, we can conclude that it's true for all natural numbers. Now, what you're going to do is you're all going to do problems 146. So you're looking at this series. You have your n, and then you have how to get the value of your term. So for the first term, it's 1. For the second term, it's 2, because you plug in 2 for n. So 2 to the 2 minus 1 is 2, and you're adding up the terms. So you have 1 plus 2 is 3 over here, 1 plus 2 plus 4 over here, and you're basically going to be proving that these terms equal this function, sort of 2 to the n minus 1. And so what you're going to do is basically like we did with the example of the odd terms. You're going to verify step 1 of the proof. So you're going to show that this part is true for this first term. And then you're going to sort of do the assumption, which is like this, except instead of n, you're going to have k. And then you're going to sort of plug in k plus 1. And then you're going to sort of tie it all together. Do a little math and then tie it all together. And then it's basically going to do the same thing over here for 147. Now, this is usually a pretty complicated thing. It might not make a whole lot of sense. But I encourage you all to attempt these problems. I'm sure you can do it. I believe in every single one of you. And that's all for today. So I will be signing off and uploading this to YouTube. Enjoy your day and your weekend. And if you have any questions, I'll be here. And let me just write it on. 8-146, 147. And I have full confidence in every one of you.